The topic we're going to discuss today involves a lot of different ideas and concepts. We will just try to have an overview of the concepts which can provide us a base to understand this conjecture. Suppose we have a set with some elements. By elements I mean anything, ranging from real numbers to matrices. We call this set G. If we take any two elements from this set and apply an operation, by operation I mean addition, multiplication, modulus, etc. Suppose the result belongs to this set, and apart from that the operation and the elements follow this property which we call the associative property. There exists an element called the identity element such that the operation involving it and any other element of the set, it returns the element itself, and for every element there exists another such that the operation between them gives the identity element. Then we call this set a group. Now let's come to something more specific. We have a set, let's say R. We plug two elements, apply an operation. Now this operation can be either addition or multiplication. Suppose we get a result which belongs to R. The associative property holds, and under addition operation there exists an identity, an inverse of every element, and under multiplication the identity property holds, but for every element we might not have its inverse. Then we call this set a ring. Now there is another property which must be discussed, that is the commutative property. If this property holds, then the order of the elements on both the sides of the operator have no effect. Addition is always commutative, no problem with that. But multiplication might not be always commutative, like in case of matrices. Fortunately, multiplication need not be commutative in rings. Now, for the case of multiplication, the identity element is unity. This can be verified very easily. For matrices, it's the identity matrix. Again, define a set F. Take two elements, apply the operation, you see the result belongs to that set F. Now the operation in this case can be addition, multiplication or division. An addition to all the properties of the ring if multiplication and division is commutative and multiplicative inverse exists in this case, then we call this set a field. Coming to order of an element of a group. If a to the power n equals 0 and a belongs to the particular set G or group G, then n is the order of a. It can be finite or infinite. Torsion-free groups are those groups where the identity element is the only one with finite order. To begin with group rings, define a field K and a group G. We define group ring as the following. Here G is a torsion-free group. Here we basically take unique elements from K for each G, multiply them and add them such that the sum is finite. Apart from this, multiplication of two elements of the ring follows this distributive property where corresponding group elements and the corresponding field elements get multiplied. We can call those elements units of a ring which belong to that ring and has a multiplicative inverse in this particular ring. Now coming to the conjecture. For a field K and a torsion-free group G, the group ring doesn't have any non-trivial units. In other words, if for any element of the ring there is another element in the ring which is its multiplicative inverse, then A is of the form K times G, where K is an element of the field K and G is the element of the group G. This is one of Kaplansky's conjecture known as Kaplansky's unit conjecture. For 80 years it was a conjecture, and finally mathematician Gilles Gardner disproved it using a counter example.